Hi, welcome to Ordinary Differential Equations. Today we are going to go take a look at notations and preliminaries for this course. So it's going to be a list of short topics, essentially as a reminder of things you might have seen in calculus. So first, functions, variables, and derivatives and their notation. Then what is meant by an order of an ODE. Next, linear versus non-linear ODE, and then y as a function of x versus x as a function of y. How do we verify a solution? Interval of solution or validity or definition or existence, they're all the same, versus what was meant by domain of a function. Then we are going to take a look at functions defined by an integral and fitting solutions to equations. So you remember that we said a differential equation is a relationship between a function and its derivatives. So the simplest of these was y prime is equal to y, which meant what's a function whose derivative is equal to itself. Well, it's good to pause for a second and just make sure we understand what is meant by these notations that we are using. So y itself is supposed to be a function of x. So typically we write y is equal to f of x. Sometimes to abbreviate even further the risk of a bit of a confusion, we might use a notation as y of x. So instead of another name, we just use the name of the output as the name of the function. And then what is meant by y prime? Y prime, of course, meant by the derivative of f with respect to x. As to spell it out clearly, here is a Leibniz notation, df dx versus Newton notation, f prime of x, or sometimes in your other classes or physics classes you might see f with a dot on top of it. That's the same thing. We typically go after a second derivative as well. In the notation of that, you remember from calculus, was something like this. And if you see it in your physics classes, perhaps with a double dot. Primes and dots are easy to write, they are very quick, but they are also a bit clumsy and hard to detect. And of course, if you want to have the 10th derivative, it would look super clumsy to put 10 tick marks on top of a name of variable. In that case, we put the number of the derivatives up here, but to avoid confusion with power, we put it in parentheses. So that means the 10th derivative of the function f with respect to x. Now it's not all that common that we are going to take 10th derivative of a function, but in engineering application you do see third derivative, so maybe you can still tolerate that. And the fourth derivative is already becoming a bit clumsy looking, but they do show up. So you make your choice as to what notation you want to use. Now y and x are of course very generic, they have no meaning attached to them. In many of our applications we are going to use more meaningful variables. So typically t is reserved for time, and then we have x, y, z for position, and sometimes in order not to discriminate between them you might use u to indicate the position, or r is another favorite to indicate position of a particle. And then the derivative of these quantities with respect to time, you remember they indicate, so velocity you remember is, for example, dx dt or dy dt or dz dt or any of them. And then you remember acceleration. Acceleration was second derivative, d2x dt2, and so on. Okay, so that's a notation for are variables and derivatives. Next up, what is meant by the order of an ODE. So this was item 2 in my list. Order refers to the highest derivative you see in an equation. So for example, if I write y double prime plus 5y prime plus say 7y is equal to 0. This is an ODE because the relationship between a function and its derivatives. Okay, what's the order of it? The highest derivative that shows up here is 2, and so the order of this thing is simply 2. Now let's write another one. I might have like x to the power of 10 y double prime plus 5 cosine of x y prime plus exponential of x times y is equal to say I don't know, say tangent of x. We have made the problem a lot more complicated by making these coefficients to be some kind of functions we are familiar with, but that doesn't have any influence on what is meant by the order. The order still is the highest derivative that you see here. For most of the semester, we are going to deal with the first order, where the cast of characters will be x, y, and just y prime, or whatever letter you care to choose, like t, y, and y prime, or whatever. Second order equations, this is going to take another bulk of our time. The cast of characters in our problems are these. As we said, in engineering, you see third order and fourth order as well. They're kind of rare, and after that you don't see much. But mathematically speaking, we can talk about nth order. Nth order, it just means you have x and y, and now let's use this notation. y1, y2 means second derivative, third derivative, and as many of these as you care to have, up to whatever order you want to have in your problem. Okay, so this is the issue of the order. Simple and sweet. You can expect that as the order goes up, just like equations in algebra that you have seen, you had linear, quadratic, cubic, and so on. As you go up, the complication increases, and we are going to have small number of cases looking at high order equations. Most often it's just first or second order. Next issue that is important is linear versus non-linear. This is highly important in applications, meaning the linear world out there are like old-fashioned electronics, and non-linear, they're represented by non-linear equations. So right now we are not going to have an easy time explaining where these equations are going to come from. It's just a matter of definition. So linear is when you take your derivatives and just use them by multiplying them with a known function and adding and subtracting them. So for example, let's write a first order linear. First order linear, you're allowed to have y prime and a y. You can take this thing and multiply it by any known function, for example, say cosine of x, or just multiply by a number. Take the other one, multiply by another known function or a number, like say 7. Make that equal to some number or a known function again. So for example, exponential of x. You are free to choose anything in these spots, so long as they are known functions or just constants. the function that we are after, y, it just shows up as itself, and then y prime also. As opposed to what? As opposed to nonlinear. Nonlinear is when you operate on y and y prime by doing just about anything. So if you write y prime squared and then say y, say 3 is equal to some function, again, it doesn't matter. So again, I have y and y prime, but they are not showing as themselves, rather you are doing an operation on them. Any power taking here, like, let's write some other example. Suppose you write sine of y prime plus y is equal to 5. So y prime is not showing up as itself, rather you are taking the sine of it. If you do anything to your function or its derivative other than multiplying by just a known function or a number, you are making it nonlinear. So here's another thing. So if you write y prime is equal to 7, that again, just the fact that you're multiplying it by itself, that makes it nonlinear. These are all examples of first order nonlinear equation. Similarly, you can have second order nonlinear equation and so on. So the recipe for linear is very strict. So you can have y prime, y double prime, and so on. As many of these things as you want. If you take them, multiplying them by known function, so not in order not to pick any specific function, let me just call this thing, say a of x, and let's call this thing b of x, let's call this thing c of x, and all of them add up to say d of x. So a, b, c, d are some known functions, or whatever you like. That will make it linear. Now, sometimes when you want to write this thing in the most general form of it, ABC wouldn't do, because, well, you're going to run out of letters of alphabet. Instead, we write something like this. We write an of x, y nth derivative, and a sub n minus 1 of x, y n minus first derivative, and so on down the line, a2 of x, y double prime, a1 of x, y prime, and then if you wish, a0 of x, y is equal to, well, I ran out of things. Let's call the right hand side, say b of x. This is nth order linear. If it fits in this mold, it's linear. If it doesn't, then it's non-linear. A lot more can be said, but at this point it doesn't help much, so we are going to postpone further discussion of this issue to future. Okay, so we talked about functions and order and linear versus nonlinear, and now y as a function of x, x as a function of y. And much of the algebra you have learned in all of your classes so far is just by tradition. Y is taken to be a function of x. Well, there's nothing to prevent you from changing the roles between these things. So it is quite natural, of course, either in algebra or in application, to change your point of view. So if you write y equal to x cubed, the implication is that you are looking at y as a function of x. Well, you can turn this thing around and write as x is cube root of y. It says the same thing, it's just that point of view has changed. How does that relate to, okay, that's basic algebra. What does that have to do with differential equation? Let's go ahead and write some equation here. So suppose I have an equation 2y prime plus 5 say equal to 0. Okay, what does y prime mean? It means dy dx, that's what it means, or dy dt, or whatever it is, plus 5 equal to 0. That's fine. Now, another customary way of writing this is 2y dy plus 5 dx equal to 0. Dx dy, when it's written like this, that's sometimes referred to as differentials. Once you write like this, you might explore the problem from a different point of view. Instead of looking at the derivative of y with respect to x, you might, for whatever reason, look at the problem from the point of view of derivative of x with respect to y. So you can write it as 2y plus 5 dx dy equal to 0. Okay, these are all equivalent forms of the same equation. You might benefit from switching your point of view. Perhaps you will have an easier time or something. So notice that this one is really the following: 5, now x prime presumably means derivative of x with respect to y. Not something that we do commonly, but it is a possibility. You should be prepared for many of your problems to be expressed to you in the following way, and then you choose to go either this direction or this direction. That's up to you, or maybe the problem might suggest one way or another. Okay, so that is the issue of changing your point of view. Now, well, what is meant by solution? Well, solution is a function that has a certain degree of smoothness, and if you plug it back into the equation, it makes it a true statement. What does that mean? So you'll have here's an example. Suppose you have a differential equation in the form of dy dt plus say 25y is equal to say 40. Well, we want to learn later on how to solve this in more complicated cases, that is, find y as a function of t that fits this bill. But right now, let's make sure what is it that we are after. So sometimes early on, some of the exercises might ask you show that, for example, y as a function of t, y of t equal to 8/5 minus 8/5 of exponential of minus 25t is a solution. Well, what does that mean, to show that something is a solution? It simply means that if I go ahead and find the required derivatives and plug it back in the given equation, I will find out that the left of it is equal to the right of it. That is, putting this thing back into the equation makes it a true statement. Well, what do I need? Obviously, here I need the derivative. Let me write it shorthand. Y prime. Well, what's the derivative of a constant? 0. What's the derivative of exponential? Let me remind everybody that you need to practice differentiation rules, and in fact make a table for yourself and refer to it in some of your problems. So exponential of u, if you want to differentiate, you remember from calculus, is exponential of u times u prime. And if you have a constant multiple, the constant multiple just multiplies the derivative as well. So this is minus 8/5 stays. Derivative of exponent is minus 25, and then exponential of minus 25t. I simplify. Well, 25 over 5 is 5 times 8 is 40. It becomes plus 40 exponential of minus 25t. This is my y prime. Well, what is 25y? 25y, 25 times that is, well, 25 times the first one is 40 minus 40 exponential of minus 25t. Well, my equation asks for adding these two, so let's go add these two. So I'll have y prime plus 25y is equal to, I'm taking this and adding to it the following. So that was 40 exponential of minus 25t, and then 40 minus 40 exponential of minus 25t. Here's the magical cancellation, and I'm left with 40, which is what the original equation was. So when I combine these things, I do get 40, and that is a vindication that this is a solution. So same issue comes up if you have more complicated problems. So for example, you might want to have the following problem: y double prime minus 6y prime plus 25y is equal to x, equal to 0. And the question is show that y is equal to exponential of 3x times cosine of say 4x is a solution. Well, now you have a bigger job in front of you, because you have to figure out what is y prime, what is y double prime, carefully apply product rule, keep track of all the entries, add up 3 resulting quantities, and show that that one actually gives you a 0. So let's go ahead and do that and be prepared for a little bit extra work. So other than differentiation rule for exponential, so let's remind ourselves again, EU prime is EU, of course, U prime. Then we need to know cosine of U. That one, of course, is minus sine of U times U prime. And then well, for good measure, let's have this for sine as well. So I have that. In addition to that, as we mentioned, there is issue of the product rule here. So if I have U times V and I want to differentiate, so of course U prime V plus UV prime. So that's what it takes to handle this problem. So again, you need to practice your calculus 1 rules of differentiation for the beginning. So derivative of the first is 3 exponential of 3x times second. Derivative of second is minus 4 sine, so minus 4 exponential of 3x, then sine of 4x. Okay, so now I have to do this thing one more time. I have to, this was, excuse me, cosine of 4x. Differentiate the first one. So another 3 comes in front, so it becomes 9 exponential of 3x cosine of 4x. Then derivative of the cosine becomes minus 4 times the 3. It's minus 12 exponential of 3x sine of 4x. Then all of that, so minus 4 times 3, minus 12 exponential of 3x sine of 4x. And then 4 times another 4 makes minus 16 exponential of 3x. Now I have cosine of 4x. Let me, oh sorry, make sure I did not miss anything. So 9 and minus 12, another minus 12, and then minus 16. We notice this is same as that. That is always the case, that we double up on the middle term, and these two also simplify. So y double prime goes through quite a bit of simplification, is minus 7 exponential of 3x cosine of 4x, and then minus 24 exponential of 3x sine of 4x. Okay, what is it that we are to do? We are taking one of this, minus 6 of that, and 25 of the original. See, if we combine them, so 1y double prime, that's a 1y double prime minus 6y prime plus 25y, what's that going to give us? Well, first one, let's write in order. Minus 7 exponential of 3x cosine of 4x minus 24 exponential of 3x sine of 4x. Then 6 of the middle term. 6 times that is 18. Excuse me, minus 18 exponential of 3x cosine of 4x, and minus 6 times minus 4 is plus 24 exponential of 3x sine of 4x, 25 of the original plus 25 of exponential of 3x cosine of 4x. So this is sort of our witch's brew, everything mixed up. When you look at it, what's happening, these things all cancel out, these things all cancel out, and here's the magic, you do get 0. Okay, so this is verification. A solution is given, you verify it's actually a solution. But how do we actually get this? Well, that's something that's going to come up a few weeks from now. But right now, what does it mean to have a solution? It's a function that you've differentiated and plug it back in the original equation. The two sides of the equation match each other. So all sorts of questions going to come up. How many of these things are there? How do you adjust them? And this and that. But let's wait for details later on. So, So we talked about changing our point of view from one side to the other side. Verification of a solution, we just talked about that. The issue of interval versus domain. Okay, interval of solution versus domain of a function. Well, domain of a function, you remember from your pre-calculus, and you practice that in calculus as well. Let's pick on a simple example. Y is equal to 1 over, say, x minus 3. Okay, you all know that something odd happens in the graph of this function. What's odd about it? At x equal to 3, something happens. Or what happens? Well, at x equal to 3, you're dividing by 0, so the function explodes. So 1, 2, and 3. We know at that point we have so-called vertical asymptote. Is that right? We need to know these things. We have a vertical asymptote at x equal to 3. What does it do? It splits your function into two pieces. One piece is here and another piece is here. Okay, what about it? X equal to 3 gets excluded from the domain. So the domain is x different from 3. So x equal to 3 is the equation of the vertical asymptote. Here's my vertical asymptote. X equal to 3 cannot be used in the equation because it gives you infinity in all the problem of infinity. So the domain is x different from 3. So in college algebra or calculus, they say what's the domain of this function? The answer is you can go from minus infinity to 3 and then jump over to the other side and then go from 3 to infinity. Pick any of these x's, pick anything from the left or right. That's a fair game. Well, in differential equation, we have a dynamic point of view, meaning we have some entity or some phenomena or something starting at a certain point of this curve and then progressing. So either going this way or perhaps going this way. Well, if you travel, you're just describing qualitatively, you are never going to get to the end of that trip. You keep going and going and going, and then forever you're stuck. So forever you're stuck either on the left side or on the right side, but you don't jump from one side to the other one. So either your solution, so you have the same asymptote and you have the same everything same as before, you are either happy with this, in which case your solution has the domain from 3 to infinity, excuse me, the interval of your solution is from 3 to infinity, meaning if at the beginning you were on that side, you're forever stuck on that side, or perhaps from the beginning you were on this side and then forever you're stuck on that side. So in this one you're from minus infinity to 3, so that's going to be your interval. Well, which one of them is it? All of our differential equations come with a certain initial point. They tell you of a so-called initial condition. It tells you at the beginning our system is this way, and so if your starting point is on the right side, this is your interval of existence or interval of validity or interval of, we had a bunch of names, intervals of, that's right, sorry, interval of solution, validity, what else, existence, and then we had one more word, interval of definition. So looks like a technicality right now until later on we come and explain what is meant by initial condition. So initial condition, just like when you do an experimental in the lab, at the very beginning you set it in a certain way and then you let it roll. That's the initial condition. Like you hold the ball in your hand, you run and throw it. At the moment that you throw it, you're in a certain place, your angle of your hand is a certain way, and you're throwing at a certain speed. Those are initial conditions. And then the ball goes into the air. After that is off your hand, and then it goes. So each differential equation has an initial condition. Then you set it up on that condition, then you let it go, and then the parameters are going to show you what's going to happen in the future or in the past, and so the interval comes out of that consideration. Okay, again, we are going to have more to say later on. We are just kind of making our feet wet by going through these topics. So that is the issue of interval. Functions defined by an integral. Okay, now this is getting a little bit more advanced now. You know, in calculus you have integration. Of course, you have integral, say, from some point to some other point, and then you have some function. Here's a friendly function, and then dt, and you have to decide where you want to stop. Well, if you want to stop at just about any point, you make the stopping point to be some variable x. Well, integral or antiderivative of t squared, that one we know is t cubed over 3. And now we are going from 3 to x. So x cubed minus 3 cubed over 3 is that answer. So here's a function, I might call it f. The function is a function of your stopping point. You do the integral, you plug your stopping point into antiderivative, and you get some answer. Okay, now that was a friendly case. Now what if I had something else? What, like say cosine of let's make it look bad, cosine of square root of t over, say, t squared dt, again from, say, 1 to x. Okay, now this is not that type of thing. I don't know how to integrate that. Probably I can try, and I could still fail, essentially due to the fact that nobody ever bothered to look at this particular looking function. T squared is so basic, somebody has already worked it out, that is t cubed over 3. This one is not such a luxurious function for anybody to be after it, and nobody worked it out. I don't know it either, and I'm not going to go spend my lifetime to figure this thing out. So whatever this is, it's a function. Just like that one was a function. What is it as a formula? Well, I don't know what the formula is, and probably nobody else does either. What about it? Still is a function. We can use numerical ways, approximate ways to figure out what that thing is, just like how we did in calculus. One thing that's important to know is what happens if you differentiate the answer. Well, that is, luckily, it's a very easy thing. If you differentiate, what do you get? 3x squared over 3, and you get x squared. Isn't it odd? This is exactly what that one was evaluated at your point x. That was essentially the point of, second point of fundamental theorem of calculus. It says that if you integrate and then you differentiate the result without knowing what the result is. If I differentiate, all I get is my original function calculated at that endpoint. So that is the fundamental theorem of calculus. Let me fundamental theorem of calculus. Sometimes they abbreviate it to FTC. Anyway, if you differentiate an integral, you end up back at the original function that you had. Sometimes you might need this thing in more advanced problems where the solution of a problem might not be as easy as these things that we always work with. sometimes we have to kind of wake up and smell the coffee that the answer to a problem is not so straightforward. Might be some function nobody ever bothered to discover or work with it. Okay, so that was another topic that we had. Going back to next issue, which was fitting solutions to equation. So again, this is a way of getting ready for things that come up later. Here's a typical question. So fitting, the issue of fitting solutions to equations. This is kind of working our way back, essentially like trying to, you pick a hammer and you have something and then you hammer this thing in some sort of a hole and hope that you plug that hole with it. Maybe you chose the right peg, maybe it's the wrong peg, but you go ahead and try. So here's a typical type of simple question. Find m so that exponential of mx y is equal to exponential of mx is a solution of say here's a simple problem, solution of y prime plus 5y equal to 0. So what are we doing? We're trying to take this thing and fit it into our equation. Well, what is like if you put a peg or a screw or something, they come with a size. It's like they're asking what screw size, what m size is going to fit the hole here. Well, if we try, see if it works at all. If this is mx, then y prime, you remember differentiation rule, m exponential of mx, so derivative of exponent comes in front. What is it that I want my y to do? I want my derivative, so I want mx. I want my y prime, let's write, I want y prime plus 5y to be 0. So y prime is this, 5y. Here's my y, here's a 5 times of that y. mx, I want this to be 0. I want this to be 0 for all x's. I see luckily that this factors, I'll have exponential of mx. I factor it. I'm left with m plus 5 equal to 0. Now this is never 0, and even if it accidentally became 0 at some point, that's not going to help. I want this to be 0 for all x's. Well, what's the easy way to do that? Here's the only way to do that. You better take m to be equal to minus 5. So we set this equal to 0, and then we say, Eureka, we find the m. It actually did work. This kind of a screw does fill in that gap, except that you have to pick the correct size for it. The m of it has to be minus 5. So y is equal to exponential of minus 5x is a solution. Go ahead and try it. Differentiate, add 5 times the function to it. You'll see it is a solution. Is that all? Is that the only solution? No. We are going to talk about that later on, like catching all the solutions. But we'll talk about that later on. 1 degree more complicated than this is having multiple variables. Here you're just plugging a hole with just one m. Sometimes there are 2 of them, and then you want to do this thing. Sometimes you want to go backward, and the equation even given to you, and you're supposed to design that equation yourself. So it says find a second order equation with family of solutions or solutions of type y is equal to, for example, ax plus bx squared. So in this case, it's asking you to design the equation. It's one level higher. It says here I give you the solutions. You go find me the equation that will have this as its solution. The only specification that I am giving you is that it's a second order equation. Why second order? Well, I have two parameters in the problem. Our previous one was m, and I have two of these things. Okay, let me see if I can leave this thing to you to work out. Let me just give you a little bit of hint. So if y is ax plus bx squared, then of course the derivative of this thing is just a plus 2bx, and then second derivative of this thing is just 2b. Okay, the derivative with respect to x of this thing is just 2b. Derivative of a is 0. Now the equation I want to write not supposed to have these parameters in it. It has no a's or b's in it. So what do? I have three equations here. From two of them I can find a and b. So for example, from here find a and b, or just find b. At least find b. Take that, let's find a and b in terms of what? In terms of everything else. Well, what's everything else? X, y, and y prime. So find a and b in terms of x, y prime. Put that in the third equation. So in another problem, if there was still an a here and a b here or something, whatever you found for a and b, plug it in the third equation. Find a, b in terms of x, y, y prime, plug into the third equation. A little bit of algebra you should do, and then you'll be all ready to go. Okay, so we talked about this backward type of questions as well. Here's a solution, find me the equation. That's a little bit odd, but it's a good exercise. So finding solutions to fit to fitting solutions to equations, we talked about that as well, and functions defined by an integral. So notations and preliminary is something to get us started and have a little bit of a review of calculus mixed in, some definitions of what we are looking at for now, and as we go on, the topics become more focused, more specific, and the list becomes a little bit shorter, but for now this is going to do. Okay, until next time, good luck and God bless.